Okay, thank you everyone. I guess I've been, for the last number of years, I've been working in sort of learning outcomes in games, and I guess the focus of today's talk will be joint work with David Easley and Yoav Columbus. I assume you guys must know who David is, sort of a senior, everyone knows him. Yoav is a postdoc with us at Yoav is a postdoc with us at Cornell. And I guess coming from sort of the distance of where I want to start from, I'm going to deviate from a large focus of what happened all of these days and not want to go to Nash equilibrium. So I've been starting to work with, how good are the outcomes or what good things happen in games when people are playing the game. And originally, price of energy was defined indeed by Nash equilibrium. But I'm going to be interested in repeated interaction. You repeatedly play the game, and you care about what happens while you're playing. So, probably in this audience, I don't have to remind you, but price of energy had a sort of long history, and I guess started with, 26 years ago, Elias and Christos defining it for Nash equilibria, and I guess the message was that you want to guarantee good performance without necessarily predicting the outcome of the game. There are multiple Nash equilibria you want to think about. I don't care which one, but they all are good. That sort of was an interesting perspective. There's lots and lots of work. I'm sure you know many more than what's on my slide that followed this up. But Nash equilibrium, as many of you, including Christos, has talked about, has all kinds of troubles. My favorite trouble is the information problem. Every player has to know who are other player and what the hell they're doing to coordinate on a Nash equilibrium. There's also the computational difficulty, as we all heard from Christos. So I'm going to focus on repeated games and learning in repeated games, and that, I'm thinking of a discrete process. Every iteration, something happens, and some outcome happens, and they try to learn. I'm going to assume that players want to do well what they're learning, and we want to think that they have additive objective functions. They average the outcomes, and they want to do well. That will be the perspective. And the two questions I've been interested in the last many years is what can we say about this process? And that will be the focus of the second one, will be more the focus of the talk today, is what is good learning? What makes it reasonable? But there are many good questions there. Learning also has an insanely long history, which actually we heard this morning, starting with Brown and Robinson, which, before I was born, not just before many of you were born, before I was born. So a really, really long history. And indeed, they were focusing on something that we heard, for example, 10 seconds ago, or the previous talk, is they were thinking of this as a process that finds a Nash equilibrium. And they were hoping that use it as a pre-play to find the Nash. The other thing I'm going to focus on is a different form of learning that has a similarly long history, is Bayesian updating. So somehow you have some prior about what's happening in this game or what you should be doing, and given your experience, you update this. I guess Bayesian updating presumably dates back to Bayes, who is a really, really long time ago. I'm not so sure that adopted in econ by Savage is a fair statement, so many of you can correct me for this, but Savage certainly was someone who was proposing Bayesian learning in game theory, and that's similarly before I was born. So similarly old in game theory, and the main topic of the talk today will be comparing these two in a setup where in markets where the comparison is reasonable. They're both doing something reasonable, and you can ask how do they compare to each other. Okay, so generally, and this is a higher level point that I definitely have been focusing on, and I think is a good point, is this change of focus. And do not think of learning as learning to find the Nash. And must think of learning as that's what's happening, and you want to do well with the learning. If you want to initially you don't know, maybe know nothing, and eventually you learn. And I want to think of this, and this is not the application today, but definitely the most convincing application, is that in applications such as where each individual step has pennies and has no consequences, but the industry is a multi-billion-dollar industry, and maybe I don't have the B right here. Some Google guys can tell me what letter I should use for how many $1 billion are involved in here. A particular ad online is nothing, is maybe a couple dollars, usually pennies. And yet, it's a multi-billion-dollar industry. So that just means that learning while playing is very reasonable. You can afford to spend some time learning. It's okay, that doesn't cost much, as long as you do well on the long term. So that's sort of the focus that I have been doing. And I guess because I'm still a theoretician, I want to say that I want to have a notion of what did it mean to learn. And instead of naming the dynamic, I want to name a property of what your dynamic has. And in the CS theory community, the popular dynamic is what was called no-regret learning. And just in case not everyone is really, really used to no-regret learning, let me start with, if I go back to Brown and Robinson, they wanted to converge to Nash, which sort of would look like this. You do something, and eventually you at least converge to a stable outcome. Stable outcome should have this property. The utility you get at this stable solution A or Nash equilibrium is bigger than a utility of any other strategy could have played instead. So I want to keep this property without keeping the stability. I guess this is what would be called no regret, and I guess the property is this. Again, the same thing, except I get rid of the stability. So I said, okay, the utility you got on average, I said that people are additive utility function, is bigger than a fixed strategy with hindsight. And I added a little bit of error, and I will actually be picky about the error. I'll come back to this in a second. The error is needed because of this learning part in the beginning. They don't know what they're doing. But, this goes up to t, and the error should not be proportional to t. Should be, usually it's root t or something even better than that. Okay, so that's what I mean by no-regret learning. I do have a slide which maybe, actually, we do know that no-regret learning converges to coarse-correlated equilibria, and going back to the discussions Christos and you had in better versions of these slides, I usually credit you with this fact, Sergio, but maybe it's wrong, I don't know. I usually credit Sergio, your paper for this fact. But that generally goes to correlated equilibria, but ignore this fact. I just want to know what happens. I don't care what the solution concept is that we're converging to. Why do I like it? I like it for many, many reasons. One is that no prior needed. Learning is doable. There are many good learning algorithms. For example, smooth fictitious play, but there are many others that all get the learners to satisfy the condition. I like to think of it, and that's maybe my favorite, as sort of a behavioral assumption. And I do have a paper now, almost 10 years old, maybe 10 years old, where we actually looked at Microsoft data where they're clearly not using fictitious play or anything of that form, but yet they satisfy the property. Like, it just seemed like if there is a fixed strategy X with hindsight, that would have been better than what you're doing. You didn't learn. There is something good to do there, and you forgot to learn. I don't care whether you used my algorithm. This property seems so natural. Hopefully you satisfied it and like it as a behavioral property. There are many good algorithms that achieve it, but maybe more dominant in the last line. It's a behavioral assumption that I, as a theoretician, can use. It's an inequality. It's very usable. So I can make theorems of the form or statements of the form that if everyone satisfies this property, then good things happen. I want to also convince you in a second or in a bit that this subtraction, the low law of t, which is usually called regret, that's how much you regret, will actually will turn out to be an incredibly important parameter. So even whether you care about regret or not, if you care about markets, you need to care about regret. That's what matters. So I'll come back to it. Again, still sort of one more background slide. So after the original Nash equilibrium definition, maybe 10 years later, there's this beautiful extension that if everyone does this repeated game and they're doing no regret learning, then the same price of energy bands, whatever we proved on this version, automatically extend to these versions. Yes?
Sorry, what is opt there?
Oh, opt is the best centrally designed strategy ignoring selfish behavior. So I want to compare, yeah, sorry, I should have said this. So what I want to do, and actually go back to this version, what I want to do is how much are you losing because it's a Nash equilibrium compared to the socially optimal solution when I can allow to tell people what to do. And it's not an equilibrium.
So for player I, it's my maximum payoff in the game.
No, it's the social optimum. Sum of the maximum payoffs on the game.
Okay, it's the value of the sum of the
Yes.
It's the maximum of the numerator over all A.
Yeah. All A's, which
All
may
A,
not be Nash.
all A,
Yes.
all A.
Yeah. Okay. So there were beautiful extensions, I guess, even if the population of the game is changing, and maybe more recently, a bunch of papers, which, by the way, I was actually originally thinking of talking about this, if you remember some original version of this 6. And then so many people heard me talk about this that I decided to change the topic. But that's another topic I'm very passionate about, and these are a current student and a past student work where one important assumption in all the previous work is that you're playing a clean copy of the game every time you restart the game, which is sort of nice if you're playing rock, paper, scissors. There's another rock, paper, scissors, and yet another rock, paper, scissors. But if you're doing adductions, then it's not a new copy of the game, because if I won a second ago, I used my money, and now I have less money. So money is a state of the game. And so these are games which actually do have a state, and the state evolves depending on what's happening. In first price auction, it's the budget, as I mentioned, and queuing, it's the number of packets in the system. There's a stateful system that the state evolves as you're playing, and yet no regret dynamic actually can do okay. So as everyone does no regret, there's something good happens in the system. But what I want to talk about today, so the message here was that no regret, or message from many of these papers combined, is no regret is a reasonable behavior, a model, it's strong enough, it implies pretty good things. Okay, today I want to talk about a different comparison, a different application in markets, and that was joint work with David and Yoav. So here is our very, 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 very simple version of a market. And hopefully those of you with strong econ background, which a large part Yoav and I learned from David as we were talking to him, we're going to take a very simple model of a market, arrow security, and you're going to have to either trust me or know it on your own. Arrow securities are actually very general. So what are arrow securities? There is some investment options in the market. 1 to n are the options where you can invest. And you can decide how to invest your money, and one of them will pay off, and the other ones will not. And I understand in real markets, they all pay off variably, and you can actually model those things with arrow securities, but arrow securities are super simple. Again, there are n options.
It's a basis.
It's a basis, okay.
Yeah.
Yes, it's a basis. So arrow securities, there are n options. There is a probability distribution Q that you unfortunately don't know, and you want to try to figure out which of them pays off with higher probability. So, this one pays with probability 50%, this one with 30, and this one with 1/6, or whatever it is. These are these arrow securities. So again, very detailed. The model is there are n players. They each have some initial vals, like let's call it W0 is the vals of W0I is the vals of player I. There's a stochastic process of which of these will pay off, which is every iteration for now is IID, and with some probability distribution S. So Q, there are S different assets, and each steps T, each of the players decide how to divide their vals, and then they're going to invest. One of them will pay off, the other ones will just be lost money, and then we're going to measure how the wealth grows. And if you did well, your wealth your proportion, I don't that much care about how much money you have, but how much you grew your wealth, or compared to other people. Do I do better than Sergio, to pick on Sergio? Like, if the answer is that, our ratios, his goes to 0 and mine goes to all of it, that's lovely, I like that. If it goes the other way around, I hate it. If we are sharing the market, that's middle ground. Okay, that's what I'm going to look at. So again, the profit that from the one thing that paid off is shared between the investors. Now, why is this an interesting market? So again, I care about...
Do agents observe other people's investments?
What?
Do an agent observe other people's investments or only its own investment?
The learning is going to be simple.
Yeah, good question. And let me tell you the 2 learning rules and how much information might be useful here. Okay, so what's the agent share? I guess if you say that, which I forgot to write here, that R and T is the nth agent's share of the wealth in the market. That's a ratio of how much money I have compared to the rest of the market. Then this is how it evolves. In one single step, previous step, I had this ratio was my share, and this is how it updates. It multiplies with, how much I invested, how much everyone else invested, and that multiplies our ratio. If I actually express this over a longer time, there is a longer product. If I care about growth rate of growth and not actually caring about the wealth, but the rate of growth, then I should take the log. And that's what I get. And what's nice about this log, so again, what I care about, if this goes to plus infinity, then the agents not only survived, but actually collected the whole damn market. If it goes to minus infinity, you're in trouble. You're getting, the other people have the market and you have nothing. But one thing I really care about, or sort of was beautiful, is that this function here is additive. This is exactly like learning people were. They cared about additive numbers over iterations. Why? Because the log of the product is an additive thing. So I could do no regret learning. And in fact, there is 2 separate literatures, which as best as I can tell, before we started to compare them, they literally weren't talking to each other. There's an econ literature on how to do this, and there's a CS literature on how to do this. So let me tell you what these literatures are. So again, that was our learning thing. I guess this version, I rewrote again this log of the product thing, but actually, I want to focus on one parameter here, because what the other people do turns out not to matter. These numbers are something you're not affecting. You're only affecting this thing. So your goal is to maximize your part of the sum. Literature number 1. Actually, maybe before I do literature number 1. What's the optimal strategy if I tell you what the probability distribution is? And again, maybe everyone for both sides of the aisle know this. But the optimal strategy is easy to figure out, because you just need to know what's the probability of what happens here and take expectations. And the optimal strategy is that you should use the probabilities as your alpha. That's your goal. Okay, that turns out, so you're maximizing the expected value, which is this thing here, and that gets maximized if you're using alpha equals Q. So your share of how to distribute your wealth should be the probabilities. If this pays with 50% probability, you should put 50% of your money in here. And if this pays with 10%, you should put 10% of your money in here. This is the optimal strategy. Now, why is this good for me? Or why do I know what the optimal strategy? It actually, because I'm a CS person, I started on the no regret side, it actually makes the no regret thing really, really sort of reasonable. No regret says that whatever you did, you should not regret any fixed strategy with hindsight. Sure, especially do not regret that one. That was the optimal strategy. Do at least as well as that one, modulo a little bit of error. Right? This actually makes no regret a very reasonable strategy to try to shoot for. And in fact, there is every book on no-regret learning, not maybe every, but almost every book on no-regret learning, there is a whole chapter devoted to this application, that, hey, there's an application here that I want to do no-regret learning in. I'll come back to this in a second. At the same time, Bayesian learning makes a lot of sense too. I evaluated you compared to what other people do, but the optimal strategy is fixed. You should just take your experience or whatever information we're feeding you and try to use Bayesian updating to figure out what the hell you want to do. So both of them make a lot of sense. And again, as best as I can tell, and I tried to talk to some people, these two communities didn't talk to each other. But they both have chapters in their books explaining how to do this. So what you should do in Bayesian learning is have some sort of prior about what this probability distribution might be and update based on your experience. Okay, so no regret, what's known? Like as I said, there's a literature here, so let me tell you what's known in the literature. The no regret word, for those of you who know no regret, usually say that, in games, what's happening, maybe you expect to have root t as your error. But turns out this is a very nice application. It's not root t, it's log t. And again, every book has it. What's special here? Not as much that they don't care so much about that there's a fixed distribution in hindsight. Turns out they don't know anything good about that. But because the payoff is the log. So they can guarantee this log t regret, even if every iteration has different Q in it. They get still log t regret, because the log is a sort of nicer function than other penalty functions. So they get log t regret, which made me feel like, oh, this is very powerful, practically no regret, like almost optimal. There is, of course, also, again, the big advantage, which I'm going to capitalize on, is no prior. Like no regret learning usually has no prior. You don't have to know anything about it. Bayesian approach, and I'm going to focus on the friendliest Bayesian approach if you have a finite prior of what the Q might be. And in that case, there is there's a simple update rule of how you update based on what you experience. And actually for this particular update rule, I'm not giving you what other people investing or not having to second order thinking of what other people thinking. Just see what happens and you can update based on that. And I guess there is an old Larry and David Easley and Larry Bloom paper, sorry, other way around. Larry Bloom and David Easley paper from early 90s, which says that actually a Bayesian investor survives even against a person who knows the market. So someone who knows Q, if you're a Bayesian learner, you're not going to be driven out of the market, which is kind of nice. So seems like Bayesian learning is good. And I guess what we want to understand, what's the comparison between these two, pluses and minuses. Okay, that's the basic setup, and here is our start of our result. So first of all, I want to claim that for those of you who didn't care about regret, I want to tell you, you really care about regret. It turns out, if I take your log of your vals, then I guess the last line, the difference between these ratios, so I guess here I changed not against the market, but two players, M and M, what their ratio is. They differ by their regret. If I have more regret than you have, then I have a higher growth rate than you have. How much higher? Exactly, the log is just the difference. So what does that mean as a theorem? So I guess the initial vals ratio is a constant, so the regret difference tells me how our grass grows. This means a couple of very powerful things. First of all, if the regret difference, it wasn't ratio, it's a difference. If the difference goes to infinity, those of you with a bit bigger regret, you're dead. As in, you get 0% of the vals. So what do I mean here? Constants matter. If I have log t regret and you have 2 log t regret, then I'll be really rich and you're going to die. As in, you get 0. So something that we're totally not used to, and as a theoretician, I know a few people who care about constants in the regret terms. In my past life till this paper, I always like, oh, whatever. we go. Ignore the constants. But constants matter. Twice as much regret, and you're out of the market. And definitely says, log t, now that's no good. Log t is like goes to infinity. If you have, one of you have constant regret, the other one is like against the optimal investor, log t goes to infinity, so I'm dying. Okay, so Bayesian learners, turns out Bayesian learners, because of the Bloom and Isley paper, actually compete well against someone who knows the market. I guess we basically claiming they survive against knowing the market, which we know from David and Larry. I also, easy to work out that they're actually going to have a constant regret. So it turns out even someone who knows the market, so knows Q, will actually have a bit of regret. And the difference is that the way I measure regret is with hindsight. With hindsight, you know, the randomness. I see the evolved randomness. And I can do, you know, say it's 50-50. But as randomness goes, one of them will have a bit more than the other, and I should have invested more in that one. Because in reality, the probabilities didn't work out perfectly. So even the perfect investor has a bit of regret, but that will be constant regret independent of t, no matter how long t is. And Bayesians survive. So it turns out a Bayesian learner has constant regret. And in particular, that means it drives the no-regret learner out of the market, despite the fact that log t was so low, it drove out of the market. This was good news for the Bayesian. Now comes good news for the no-regret learners, with some questions afterwards. If you're Bayesian, but you're not perfect, turns out you're host. No-regret learner was much more flexible. So here is a couple of ways no-regret learners are flexible. What's an imperfect Bayesian? We're offering two versions of this. One imperfect Bayesian just has the prior wrong. So it's a little bit wrong, like it's just a little bit wrong. And second imperfect Bayesian is not doing his updating very perfectly. His arithmetic is mistaken. Maybe it occasionally, he overweighs the prior, and sometimes he underweighs the prior. We can even do this with his expected update is correct. He just varies a little bit. He's noisy in how he's doing the updating. The first item is easier to show you, so I can easily show you. Certainly, you might feel that the Bayesian people are silly here. So say, for example, there are two possible states of the word named A and B. You know, either then the correct distribution is this one that, you know, A pays with probability 78%, the other one with 22%. Your prior thinks that it's a 0.1, 0.2, one of those things. So unfortunately, the truth is not in your prior. What a Bayesian will do is, say, starting from 50-50 is this unfortunate process. That is, there is the truth. And the silly Bayesian, starting from 5 has an exponentially fast convergence to what is the closest number to the truth. But he's very resistant, despite seeing something that, no, I know my prior, 0.8 is the closest option, that's what I believe in, which means that after you converge exponentially fast, you unfortunately have a constant error all the time. And, you know, collecting linear regret. Whereas, remember, the no-regret learner only has log regret, so it's better off. Maybe a little bit harder to see the second one, and I don't want to show you, but that's also true. If your updating is a little bit noisy, same problem. You're getting linear regret, and even a root T regret will kill you, but the log T that the no-regret learner can do is much better.
What about I don't know how, I'm not sure whether it makes sense. What about you may also want to incorporate errors into the no-regret?
Yeah, they're less sensitive to no regret, to the update error. So that is the second result. The no regret learners don't have a prior, so they can't have the wrong prior because they don't have one. But in the update, they're less sensitive to update mistakes than than the no regret, so they're better in that sense. Okay, but here
is
is...
the property of discreteness that you keep it fixed. You are not allowing them to change, to adapt the grid.
Yeah, let's come back. It's a great question. Allow me to come back in a second. So I guess here is one positive best of both worlds thing we would like to offer that somehow can do something that neither of the two sides can do, and maybe sheds light of what might be better behavior in the future. So if I don't make the assumption that the distribution is fixed over time, which in real life maybe it's not. You know, a couple of times, like for a while it's Q, and then it becomes Q prime, and then it becomes Q double prime. There's a slow shift. Doing really well in a market that non-stop changes, that's hard for anyone. But doing well in a market that has a couple of shifts, you know, rarely, but sometimes shifts, the no-regret learners do very well with that. So there is natural extensions to no-regret algorithm. If the K shifts, they collect K times log T regret. And they don't have to know where the shifts occur. They don't have to know how many there are. They can just adopt. If their shifts occur, basically it costs them another log T. But that's all, which is very nice and makes it more flexible to not super steady environment. Unfortunately, they collect the log T already in the beginning because they don't have the prior. And Bayesian learning has constant regret without the shifts, but it turns out once the shift occurs, it corrects linear regret. And one thing that the Bayesians are doing wrong, which maybe was visible on the demonstration slide I had, that they so got stuck on believing that 0.8, even if it was even more if it was actually correct. That when it shifts, it takes them a long time to get rid of it. So here is a proposal, which is a trick that the CS community have always used very heavily, called regularization. Don't converge so fast. Here is one version. You do a Bayesian updating, like you always did. But I want to add you sort of a noise. At time t, I want to add you 1 in t squared, you know, randomize. You're not so sure yet, or something. If you do this, it turns out, because 1 in t squared is a property that sums to a constant when you sum over t, unlike 1 over t that didn't do that, that is good enough in both sides, that is, gets k log t regret with k shifts, but get constant regret if there are no shifts. So sort of combining both of the best words here. Regularization is a standard learning trick. When you talked about smoothed fictitious play, then that's kind of what they're doing. They're regularizing fictitious play, or at least one way to deal with it is regularizing fictitious play. It's a standard trick in CS, and it's very, very helpful. It sort of keeps you open to things changing over time, which...
So that smoothing is done once and for all at the beginning.
No. It's every...
Smooth fictitious play.
Yeah.
Smooth fictitious play is a fixed smoothing that you do at the beginning and not every period.
That's debatable, and we can come back to that debate. Some version does that, but then the opponent can take advantage of you. If you want to be stable against an opponent that might want to take advantage of you, better off if you randomize every iteration. Sorry.
Okay.
Okay, so that's sort of, you know, the message is what I already said, is that 1 over t squared error has the property that 1 over the t squared sums to a constant rather than summing to infinity. That's an error we can tolerate, and that's sufficient to cause the convergence. If you don't need the exponential convergence that Bayesian learning on its own would do, which then makes it too sticky. To summarize what this part of the message, or this paper is trying to say, I really like the red sentence up there, that first of all, the two sentences, one is blue, one is red, that regret really matters. Turns out regret is the thing that measures whether you survive or not, very sensitively, more sensitively than I ever looked at. Constants matter. You can't, twice as much regret is not good. Only if the difference is bounded is when you can survive. You need the regret to servers. Bayesians and no-regret learners have some trade-offs, especially with a finite Bayesian, which is my answer to Sergio's thing. If I give the Bayesian continuous prior, like they say, they can be anywhere between 0, 1, or something. Turns out the standard Bayesian updating is one of the things that learners do, that the learning algorithms do. They're literally the same algorithm. That's the multiplicative weight-based algorithms are actually Bayesian updating there. So then they're kind of doing the same thing, then getting the same log T regret. And regularization really helps. Coming back to the broader message, and I'm going to maybe end with this, I generally, I like no-regret learning. I have a lot of papers that use no-regret learning, but I guess one question I have been asking for the last many years in giving talks is, can we do something better in concrete games? And in this particular game, we actually, have a proposal that Bayesian updating with this regularization is better than classical no-regret learning. No-regret learning is sometimes too simplistic, and we should aim to do better. And there are lots of cool questions there, one of which is because I want to use whatever my rule is, not as an update rule, but as a behavioral rule. I want it to be true that data tends to support it. Like something algorithmically doable, and whether my complicated algorithm is what people do or not, the data tends to have this property. That's a good question, and I continue to like it as a question, and will thank you guys, and that's all I wanted to say. Oh, sorry.
Very interesting, Eva.
Oh, hey.
One question I had is that given that constants are so important, I wonder, is it an interesting direction to think about models that at least come with some robustness? Because, if constants are so critical, I mean, in very few phenomena we know constants in the universe, right? So.
Well, I mean, robustness is a little bit where we are shooting with the changing.
Yeah, but then again, you had order k log t for, the Bayesian that's updating, and another order k log t for that no-regret learner with shifts, and now, again, there are some constants in the order, and
Yeah, so. Excellent point. Good question, and I don't have a good answer.
Yeah, okay.
But I did admit that, in the no-regret community, there is this guy, Gerger Neu, who always writes papers with improving the constants. And I like Gerger, but somehow I was ignoring all these papers. So.
You must know this saying that constants aren't and variables won't. But variables won't vary and constants aren't constants. No, but now, serious question. Isn't the reason that constants matter here is that you really looked at regret relative to the log? So everything gets magnified by becoming exponential. So any small change, it's now, so if my ratio is, if I grow at 1.1 and you grow at 1.10001, that's it. In the long run, you are winning and beating me completely. So that's really the reason constants matter. If you were to compute regret relative to the original payoffs, let's say, then constants will not matter relative to that thing. So what I'm trying to say, maybe this is very much model-driven. Model is correct for this model, but in other models, that's no longer true.
It is true that anything I said is very driven by that I'm using at growth rate as my model. And if I don't take the log, I have this product thing, and then, I don't know, all kinds of things matter. But I don't buy your example. If I care about the original objective function and not the rate, if I'm growing at a 0.0001 faster rate, I will drive you out of the market. You will have nothing, and I will have everything. So it will matter. But you are asking a great question that we thought about, and at the moment, I don't have a good answer. There are other reasonable ways you can measure what you want, not just growth rate or share of the market. But I thought share of the market is both a reasonable measure, and again, 2 big communities write a lot of papers on your share of the market.
It's the right way to do is to take the log and look at the growth rates. That's clear. But in other models, maybe that's not the right thing. That's what I'm saying.
Yeah, you're right.
Thank you for the very interesting talk, Eva. What about negative regret? So especially if I suspect, if I understand the model, that when the target is time evolving, then maybe negative regret should be possible. In that case, shouldn't maybe this give an argument for using, let's say, more aggressive algorithms that are not no regret in the general case? Does that make sense?
Yeah, so I guess I swept something under the rug, and I don't know if I'm going to go back. Maybe that's too complicated. In the version with shifting behavior, I measure, regret is measured against that many shifts. So, I want to have regret against, there were k shifts, and my comparator is how do I do against something that shifts k times? Or at least that is what the k-log people, that's the no regret people can guarantee that even, against the truth, which shifted k times, or against anything that shifts k times, they don't have more than k-log t regret. And that's what we generate by adding the regularizer, that against the truth, against the actual what happened, you don't have so much more regret. You're right that people can do better than getting no regret, and negative regret should be helpful here. And our theorem about how your growth rate is really the difference in regret, what matters, is not sensitive whether your regret is positive or negative. So if the situation is stable and you actually manage to get negative regret, lovely.
Okay, thanks very much again.